That's amazing, right? No. Yeah, sorry. So anyway, so we have this model, right? And we can compare it to data. And so we measure the temperature, we measure the temperature correlation with the polarization, we measure the polarization, we measure it with different galaxies. No matter how we do it, we get the same model, and that leads to our same basic understanding of the universe.
Yeah, I thought in your book, and just now you mentioned that we also have kind of a galaxy distribution to shape our understanding of the evolution of our universe. Can you tell us some perspective of how we can kind of combine the measurements of the galaxies and the cosmic microwave background to kind of have a more precise understanding of our universe?
Sure. Yeah. So, right. And if you remember that picture I was telling you about, so if you look at the microwave background and look at the fluctuations, there are all these hot and cold spots, right? And those are the seeds of the formation of clusters of galaxies and galaxies. And they're hot and cold because the strength of gravity is ever so slightly different in those spots. And so if this gravity is a little stronger here because gravity is only attractive, if it's a little stronger in this spot in space, it's going to pull matter into it and it's going to clump up. It's the gravitational instability. So matter is going to clump up, and that clumping up is the structure, clusters of galaxies and things like that. And the way to sort of put it all together in your mind is that the microwave background, it's the oldest light in the universe, so it comes from furthest away. The galaxies are between us and the microwave background. But the same physical process that made the hot and the cold spots in the microwave background gave rise to all the galaxies. So if we understand the universe from the microwave background point of view, we better understand the distribution of the global, not individual, but the overall characteristics of the distribution of galaxies. And that works out really well, right? That works. It's amazing. But then there's another level of depth to this. So here's the microwave background out here. Here are the galaxies. And the light from the microwave background we can think of it as traveling across the universe till it lands in our detectors. But when it does that, it goes by galaxies and clusters of galaxies. And Einstein told us is that when light traverses a massive object, its trajectory is bent like a lens with, in a telescope and binoculars or your glasses, right? It bends the light. And there's a very, very clear prediction, right, that connects, that you can say, okay, if we have the right picture of the universe, we can now look at these galaxies illuminated by the microwave background behind and get a precise prediction for how much the light is bent on average. So there's a direct connection from the whole model. And you can go and measure it, and you are bang on the prediction. It's stunning, right? So here's this, to put this together, right? We're looking at light from vastly different stages in the evolution of the universe. And our model says there should be this deep connection through thinking about Einstein's general theory of relativity. And it all hangs together. And so, because then it goes and hangs together, and you say, wow, we know this. This picture holds together, and then it becomes a tool. And so now, once that comes together, you now have this new tool, and we can start to look for tiny variations. For instance, one of the things that we're doing right now is we're looking for this tiny variations in how light bends around clusters of galaxies to see if the universe is full of neutrinos. Well, we know it's full of neutrinos, but even to look it should be sensitive to the mass of the neutrino, which no one's ever measured before. We know these particles exist. We know there should be about as many per square centimeter as there are photons in the microwave background. We know they exist on Earth, but we don't know their mass. We know their mass differences, but no one knows their absolute mass. But cosmologically, this lensing has now become a tool, and we can use it to study these concentrations of mass at large angular scales for neutrinos clumping. So anyways, this has sort of been the process over these past decades, just to figure out these sort of deep connections like this. And then those become a tool for learning yet something new about the universe. So it really is, it's like the universe is becoming a very small place from the point of view of cosmology, right? Where it just hangs together so well. Lots of open questions, no doubt about it, but the puzzles are really, the pieces of the puzzle are really, really coming together.
Yeah, I think in your book you mentioned, you explained how this kind of lensing kind of effect have some effect on the cosmic microwave background. And can you tell us how you can kind of deduct the effect of lensing from the CMB?
It's okay, so this will be maybe a little too detailed, but I'll take, you can, if you held up, shower glass, are you familiar with that term? Glass that people often have in their shower that's patterned, so you can't see through it very clearly. If you held up a perfect sphere behind that glass and you knew it was a perfect sphere, you could tell what was going on with the glass by looking at how that sphere was deformed. And so, right, so you can deduce it. So that stretches the analogy a little bit. But what we know, because we can tell this other ways, is the statistics of the microwave background, the statistical distribution of the fluctuations. We know it's random character. And what happens is when it's lensed, the microwave background is lensed, it alters the statistics. And it alters it in a way that we can separate it out from the fundamental statistical distribution in a very characteristic way. And so roughly, that's it. The patterns shift in just the right way to be able to separate it out from the intrinsic microwave background. I don't know if that helps. It's a little abstract, but if you're good, you're a theorist. It's the 4-point function, right? The microwave background, intrinsic microwave background doesn't have a 4-point function. It has it's a Gaussian random field. It's completely described by the 2-point function, right? So lensing adds a 4-point function, and you can separate the 2-point function from the 4-point function.
Yes, and I heard that in the ground-based experiments, and they need to take into consideration about the influence from the atmosphere. And you know how to do that, or?
Yeah. No, actually, okay. So, yes, because. The simplest picture is, so the atmosphere is just a temperature fluctuating above you. Okay. And the fluctuations, you can edit this out. This is for you. The fluctuations are Kolmogorov. Okay. Which means that there's much less fluctuation power at small angular scales. And this is why you see, for the ground, at very large angular scales, there are lots of fluctuations. And so they really are of a fraction of a degree. So that's why you can't measure large scales from the ground, in addition to the systematic effects I was telling you about before. But if you go to very small angular scales, the fluctuations are much less. And then what you do is the way to view it is they are just fluctuations. And if you have a random fluctuation and you look at the sky long enough, it just averages out, right? As long as you know it's random, it just averages out. And so essentially that's what we do. And then we make sure we look at the statistics of the data to make sure indeed it's random and averaging it out. And that's, when we do tests before we publish a result, that's absolutely a critical one. So we make sure it's averaging out.
The key point is you have a long period of time so that the noise is just average out.
It's random. Yep. And two things. It's that, and then plus we look at small enough scales, right? Where it's, I don't know how much it goes down. It's Kolmogorov, so it's k to the minus 8/3 power. So it's really dropping quickly, and so that helps a huge amount. So if you look at all these ground-based experiments, you see that they really sort of kick in above some angular scale, and that's why. That's one of the reasons why. But it also, you can tell because the fluctuating thing in the atmosphere is really water density. And so that's why these experiments, there's one going into Tibet. There's one, ours are in Chile, really very high, 5,200 meters. And then at the South Pole where it's very high and dry. So you go to places where there's not much water, or on a balloon, or of course on a satellite, just to get above the whole atmosphere. But you want to go to places where there's no water because that's what's fluctuating.
The questions are becoming deeper and deeper. So
sorry.
Right.
I mean, these are hard. These are not easy to. These are not.
Yeah, maybe. Right. Maybe we also ask some softer questions, such as when you are doing popular science. What are the questions that people ask you most?
I think it's what really people have a difficult time coming to terms with is just how to think about the universe as a whole.
Yeah.
And how, because we've all heard this term Big Bang.
Right.
And it really just gives the wrong image, right? All of a sudden you hear Big Bang and you think of firecracker.
Right.
And that's not it. Right?
Yeah. And this is
and so you then that immediately, once you hear firecracker or something like that, you think that there's a center and and it's growing or something like that. But it's just not the way to think about it. And a better way is to one say, what do we know? As far as we can tell by measurement, the universe is infinite in extent. It doesn't, of course, we can't measure out to infinity. We can only measure a finite fraction. But as far as we know, it goes on forever. Or a more precise way to say that is we cannot distinguish the data from a universe that goes on forever. The data can't distinguish between those two options. So the two options being it's infinite or just really, really much bigger than we can see. So that's sort of one bit. And then the other bit in there is that, remember, because everything is going away from each other, apparently flying away from each other. I don't have time now. I mean, that looks the same no matter where you are in the universe, but you can just roll that picture back. So that says the universe has to have a finite age. And light travels at a finite speed. So that means if this whole landscape, we only have access to a fraction of it. What we call our Hubble sphere, if you will. So we can only see that much. And over that region, we can't tell the difference between a very, very, very large universe and an infinite one. Okay, so once you're there, then, and I should say, nature did not have to be that way. If it were different, we could have told through measuring the microwave background. This is the universe we have. So once you have that picture, then just imagine it, the whole universe, expanding and contracting, and going back in time. It's just smaller. Just everything's closer together, but always infinite. So it's just a lot more dense, and we only have access to some small fraction of it. So I think that's a much easier picture. And then you realize that there's no edge you could possibly ever see, because no matter where you are in the universe, you have the same picture. When you say size only means one thing. It's the size inside our Hubble patch, or Hubble radius, right? When we say size, that's all it means. It's otherwise, we have to say it's super big or infinite. We don't know, right? So that I think is probably the most difficult thing to get in your head, to start thinking about it that way.
Yeah, I think this is a very important message also to the Chinese readers of your book, because actually this is one of the questions I was also asked the most. And also there is, in China, there is a additional confusion, because all by chance, singularity. So people know cosmic singularity, but singularity in China was translated in another way, which is singular point, which is the translation from black hole physics, I think. Yes. People really think that singularity is a point, which is really more about to clarify. Yeah, thank you very much for clarifying.
No, I would say even, we go back to where physics breaks down, right? And there's not, in their model, I think the most popular model for the beginning, you go back a little further, you always go back to when physics breaks down, is this period of inflation where all of a sudden space expanded exponentially quickly. But I think there are a number of models. That's certainly the most popular now, but maybe the current universe is one cycle that we're in. I'd say that's not, a lot of people think that's a good model, and it's possible that measurements will show us the way to which one of those is more likely. We'll see from ongoing measurements. But the other thing, and let me just give you another sort of visual image that I think helps put the universe in scale. So here we are. Two things. Here we are. So what happened? So the Big Bang in this picture I just told you happened everywhere, right? So on our watches, so there's nothing funny about time. If we could live in this incredibly dense, hot, inhospitable state, if our minds could be there anyway, right? On our watch, the Big Bang is happening right here, in China too, but in Princeton and China, everywhere. It's happening everywhere on our watch. And every place in space goes through the exact same process, no matter where you are, right? It's just time ticks away. Time ticks away. Universe expands, you see things moving away from you. No matter where you are, you see things moving away from you. It goes on. Right here, right around the Earth, the microwave background, there's this period called decoupled from the atoms about 400,000 years after the Big Bang. That happened everywhere in space, same time, everywhere. And it marched on. Every structure then formed right around us. We're in structure. We know it formed right here. So it all happened right here. Now, if you can, and so now here we are, we're looking 13.8 billion years later from this process starting. We look out, right, and we see the microwave background far away. The light that we get has been traveling to us for about 13.8 billion years. Okay. Out there, right instantaneously right now, the universe looks like it does right around us. if you could suddenly be transported to the edge of the observable universe. And for someone out there looking back, they would see the microwave background coming from where we are now, right? Because for us, it was liberated, 13.8 minus 400,000 years ago, right here. And it's been traveling 13.8 billion years. And that's the radiation that was here is now out at the edge of the observable universe. So if you hold all those things in your head, I think that's a good way to sort of put it all together. And you can see that no place is special. That time doesn't get weird. It's not weird. It's just what you measure on your watch right here. And then the whole universe just evolves and keeps evolving.
Right. Yeah, that's a really important message.